Hello, welcome back to Short Lectures in Physics, and the topic for discussion in this session is planar motion, that is two-dimensional motions. So far we have seen the one-dimensional motion in which a body moves along a straight line whose positions and equations of motion have been described in terms of its coordinates along the x-axis or y-axis or z-axis of the coordinate system x, y, z. Whereas the description of a body in a plane, that is planar motion, needs mentioning any two of the coordinates like x, y or y, z or zx in the xy plane or yoz plane or zyx plane of the xyz frame of reference. Thus, physical quantities in planar motion analysis need to be considered as vectors. Position of a body at any instant of time is denoted by its coordinates xy or yz or zx at that particular instant of time. If a body covers equal distances in equal intervals of time, however small the intervals of time may be, that means take the interval of time as small as possible, that's what it means. Then the body is said to be moving with uniform or constant velocity. Then its path in a plane follows a straight line. If the velocity vector of the body changes by equal amounts in equal intervals of time, again however small these intervals of time may be, then the body is said to be moving with uniform or constant acceleration. That means we have defined a motion of the body in a plane with uniform or constant velocity and uniform constant acceleration. Then when it is moving with the uniform or constant velocity, path is straight line. When it is moving with the uniform or constant acceleration, its path follows a parabolic form. Consider the motion of a body moving with the uniform velocity in xy plane. Its position in the plane at any time is given by its coordinates, rectangular coordinates x, y. Let its position be at point P with coordinates x1, y1 and at time t1, and at Q with coordinates x2, y2 at time t2. So its location with reference to the origin, that is 0, 0 coordinates, can be presented by the position vectors r1 bar and r2 bar. r1 bar is the vector OP bar at time t1 and r2 bar is OQ line, OQ bar at time t2. Then the displacement in the time interval t2 minus t1 is given by the vector pq, that is denoted by r bar. So from triangle of vectors, this OP plus PQ is equal to OQ, that is R bar is equal to R2 minus R1 bar. That is difference in position vectors at time t2 with reference to time t1 is giving the position vector of the displacement vector of the object. In terms of position vectors, the displacement is then given by R bar is equal to x2 minus x1, that is the difference in displacement in the x direction, x2 minus x1 unit vector I bar plus y2 minus y1 unit vector j bar. Similarly, velocity is given by displacement by time, that is r2 bar minus r1 bar by t2 minus t1 is the time difference. In terms of rectangular coordinates, the velocity vector is given by vxi plus vxj. That is, vx is the velocity component in the x direction, vy is the velocity component in the y direction, and which is presented in the unit vector notation. Hence, v bar, magnitude of the v bar is given by square root of vx square plus vy square. Then its equation of motion, if we see, v bar is equal to r2 bar minus r1 bar by t2 minus t1 we said, that is equal to r2 bar minus r1 bar by t, that is r2 bar is equal to r1 bar plus v bar t. In rectangular coordinates, r bar can be presented as x2i plus y2j, and r1 is given by x1i plus y1j, plus v bar is given by vxi plus vij into t. That is x2i plus y2j, that is final position, is given by x1 plus vxt I bar plus vy1 y1 plus vyt j bar. That is the position of the object at time t2 with reference to the position at time t1 and the velocity component. So from the above, we can say that the two-dimensional motion of a body in a plane with uniform velocity is a combination of two one-dimensional uniform motions of the body along two perpendicular directions. That is, v bar is equal to vxi plus vyj. That is the concept. Then path of the object, if you want to see, we have x2 is equal to x1 plus vxt and y2 is equal to y1 plus vyt. That is position of the object at time t2 along x direction and y direction. Thus t is equal to x2 minus x1 by vx. Thus y2 is equal to y1 plus vy by vx into x2 minus x1. That is, it is in the form of y is equal to mx plus c, which is represent the equation of a straight line. Thus the path of the body moving with uniform velocity in plane is a straight line. Now consider the motion of a body moving with uniform acceleration. So far we have seen uniform velocity. Now let us see what happens when bodies moves with uniform acceleration a bar in the x-over plane. Now we are presenting the velocity components along the x-axis and y-axis with reference to time. At time t1 the object is at p, at time t2 the object is at q. So the coordinates of the p are x1 y1 and q x2 y2 at times t1 t2 as mentioned earlier. Its velocity in a plane is represented by its rectangular coordinates vx and vy. So velocity at a particular time is represented by its position vector, that is v1 bar is equal to op bar at time t1 and v2 bar that is oq bar at time t2. Then change in velocity in the time interval of t2 minus t1 is represented by the vector v bar, that is pq bar. If we follow the triangle of vectors, then v1 v2 v bar can be given by difference in position vectors v2 bar minus v1 bar. So acceleration is given by rate of change of velocity. So a bar is equal to v2 bar minus v1 bar by t2 minus t1. In terms of position vectors, again if you write change in velocity v2 bar minus v2 bar v1 bar can be written as vx2 minus vx1. That is along the x direction velocity components at the time t2 and t1. So change in velocity is given by vx2 minus vx1 I bar plus vy2 minus v1 j bar in the two perpendicular directions. In terms of rectangular coordinates, a bar is given by axi plus ayj, because vx2 by vx2 minus vx1 by t2 minus t1 is ax bar, vy2 minus vy1 by t2 minus t1 is ay bar. So these are the two acceleration components in the x direction and y direction. Thus in rectangular coordinates a bar is axi plus ayj unit vectors, hence modulus magnitude of a bar is given by square root of ax square plus ay square. And the equation of motion with reference to acceleration is concerned, we have a bar is equal to v2 bar minus v1 bar by t, that is v2 bar is equal to v1 plus a bar t. In terms of rectangular coordinates, v2 can be written as vx2i plus vy2j is equal to vx1i plus vy1j plus axi plus ayj t, that is vx2i plus vy2j, that is the velocity vector at time t2 is equal to vx1 plus axt I bar plus vy1 plus ayt j bar. Thus two-dimensional motion of a body in a plane with uniform acceleration again can be seen to be a combination of two one-dimensional uniform motions of body along two perpendicular directions, that is vx2 bar is equal to vx1 bar ax plus ax bar t and v by 2 bar is equal to v by 1 bar plus ay by t. The two components in the line axi plus ayj. The path of the object, if you want to see, p average bar is equal to half of summation of two position vector, that is v1 bar plus v2 bar by 2. That is equal to half v1 bar. v2 bar can be written as v1 bar plus a bar t. That is equal to v1 bar plus half a bar t. Also, v average bar is equal to r2 minus r1 by 2, that is in terms of displacement of the position vectors. Thus, r2 bar is equal to r1 bar plus v average bar t. So, r2 bar can be written as r1 bar plus v1 bar plus half a bar t into t, that is equal to r1 bar plus v1 bar t plus half a t square. In terms of rectangular coordinates, x2i plus y2j, r2 bar can be represented as x2i plus y2j plus is equal to x1i plus y1j plus vx1i plus vy1j t plus half axi plus ayj t square. So that after simplification you will get x2 can be written as x1 plus vx1t plus half ax t square, and y2 is equal to y1 plus vy1t plus half ay t square, which is in the form of second order equation in x and y terms. Thus the path of the body moving with uniform acceleration in a plane follows a parabolic path. Then, so far we have seen uniform velocity, uniform acceleration. Now we will see uniform motion in a plane. When velocity and acceleration of a body moving in a plane changes with time, then it is said to be moving at non-uniform motion. It is in non-uniform motion. In such cases, average and instantaneous velocity as well as acceleration values are to be considered. The path of the body will be curved. Let the body be moving in a xy plane with non-uniform velocity. Let the coordinates of the position be again xy at time t and x plus delta x, y plus delta y at other time t plus delta t. Why you are taking delta t? The intervals of displacement or time to be as small as possible. Let the respective position vectors be r bar and r bar plus delta r bar. So average velocity of the body is given by v average is equal to delta r bar by delta t, and instantaneous velocity of the body at any position is given by v bar is equal to limit delta t tends to 0 delta r bar by delta t. So that can be represented as a differential form dr bar by dt. In terms of rectangular components, E bar is equal to d by dt of r bar, that is xi plus yj. So d by dt of xi plus yj is equal to x di by dt plus dx by dti plus y dj by dt plus dy by dt j bar. di by dt differential and dj by dt differential become 0 because they are unit magnitudes. So that becomes dx by dt I bar plus dy by dt j bar. So dx by dt is nothing but vx, velocity component in the x direction, dy by dt is the velocity component in the y direction. So v bar finally reduces to vxi plus vyj. So magnitude is given by square root of vx square plus vy square. Angle between the velocity vector and the x-axis is given by tan alpha is equal to vy by vx. Average acceleration is given by A average is equal to delta v by delta t, again following same steps like average velocity and instantaneous velocity procedure. Instantaneous acceleration is given by a bar is equal to limit delta t tends to 0 delta v by delta t, that is dv bar by dt. In terms of rectangular component, a bar is equal to dv bar by dt, where that is d by dt of vxi plus vyj, where vx and vi are the velocity components in the x and y directions. That is equal to dvx by dt I bar plus dv by dt j bar. Dvx by dt is ax and dv by dt is ay. So a bar is equal to ax I bar plus ay j bar. Further, ax is equal to dvx by dt, that is d square x by dt square, and Ay is equal to dv by dt, that is d square y by dt square. That is second differential of displacements. First they are the differential of velocity. If we consider three-dimensional motion in space, then position of an object or a body in three-dimensional motion can be described by all the three coordinates in the XYZ system. The coordinates are XYZ. Position vector is given by r bar is equal to xi plus yj plus zk, and its magnitude is given by square root of x square plus y square plus z square. And in this case, the instantaneous velocity is given by v bar is equal to dr by dt, that is equal to d by dt of r bar, that is d by dt of xi, yj, zk. Following the same procedure, you can show that v bar is equal to vxi plus vyj plus vzk, and magnitude is given by square root of vx square plus vy square plus vz square in terms of the scalar components of vector v bar along the x, y, and z directions. And its instantaneous acceleration is given by a bar is equal to dv bar by dt, that is equal to d by dt of v bar, that is equal to d by dt of vxi plus vyj plus vzk, that is equal to dvx by dt I bar, dv by dt j bar plus dvz by dt k bar, that is equal to axi plus ayj plus azk. And its magnitude of acceleration a bar is given by square root of ax square plus ay square plus az square in terms of scalar components of a bar along x, y, and z directions. Let us see some numericals to understand the points discussed so far. Let the coordinates of a particle be varying with the time as x is equal to t cube minus 32t and y is equal to 5t square plus 12. Then let us find out the position, velocity, and acceleration at the time of 3 seconds. R bar is equal to xi plus yj, because it is a two-dimensional motion we are discussing. R bar is equal to xi plus yj, that is equal to t cube minus 32ti plus 5t square plus 12j. At time 3 seconds, R bar is equal to, if you substitute in place of t the 3 seconds, you will get it as minus 69i plus 57j. So Vx bar, velocity if you want to find out, dx by dt is equal to d by dt of t cube minus 32t, that is 3t square minus 32. At time 3 seconds, Vx is equal to minus 5 meters per second. And Vy dy by dt is equal to d by dt of 5t square plus 12, that is 10t. At time 3 seconds, Vy can be shown to be 30 seconds. Thus, V is equal to minus 5i plus 30j, substituting the Vx and Vy components. Then Ax is equal to dvx by dt, that is d by dt of 3t square minus 32, that is 60. At time 3 seconds, Ax is equal to 18 meters per second square. Ay is equal to dv by dt, d by dt of 10t, that is 10. At time 3 seconds, Ax is equal to 10 meters per second square. That's A is equal to 18i plus 10j. Another numerical, let a particle starts from origin at time 0 with a velocity 10j meters per second and moves in xy plane with constant acceleration of 8i plus 2j meters per second square. Time at which the x coordinates of the particle will be 16 meters. Then its y coordinate of the particle and speed of the particle at that time also will be find out. The position of particle at any time t is given by rt is equal to u naught t plus half at square. U naught is the initial velocity. That is rt is equal to 10 j t plus half times 8i plus 2j t square minus 4t square I plus t square plus 10t j, substituting the given equations. Xt is equal to 4t square and yt is equal to t square plus 10t. It is given xt is equal to 16 meters. We want to find out time when the xt is equal to 16 meters. Thus, time is equal to square root of 16 by 4, that is square root of 4, that is 2 seconds. When time is 2 seconds, now we know the time when the x coordinate is 16 meters. Then the vertical distance of the particle is equal to y2, that is at time t is equal to 2 seconds, 2 square plus 10 into 2, that is 24 meters. Velocity of the particle vt is equal to d by dt of rt, that you will get it as 8ti plus 2t plus 10 times j. Thus, velocity of the particle at 2 seconds is equal to v2 is equal to 16I plus 14j. Magnitude of the velocity of the particle time 2 seconds is equal to v2 is equal to root of 16 square plus 14 square, that is 21.3 meters per second square. Hope this will give you some insight into the planar motion analysis of bodies. See you in the next session. Till then, bye.